All right, so as Brett said, the title of this talk is C++ Today, the Beast is Back. That is, my name is John Taub, and this is the book that I wrote with Casper Asman. And kind of the story of the book is part of what the talk is about. Right? The existence of the book is what the book is about, in a sense. And that's that O'Reilly paid us to write this book. They didn't pay us very much, but they paid us to write this book. But they give the book away free. If you go to this URL, you'll get a free copy of this PDF. And when they actually printed real books, they actually were passing those out at conferences entirely free. So one possible theory is that Tim O'Reilly is a complete idiot. He's paying somebody to write books that he gives away free. How many of you think Tim O'Reilly is a complete idiot? Okay, not the case. Oh.
You gotta have somebody.
Yeah, there's got to be one, right? No, that's not what's going on at all, right? So this book, and I wish I brought a copy. It's like 60 pages. Better to call a booklet, maybe. They actually call it a report, and this is part of their business plan. They do, in fact, publish these reports when there's some hot new technology that's coming out. They publish a free report so that they can get a taste of the market and develop email addresses that they can market new books that aren't going to be free, longer books with more detail, to people who are interested in the free books, right? It's a marketing technique. Notice I said hot new technologies. Let's see, C++ starts in the late 70s. Some people's book, that's not a hot new technology. But the fact that O'Reilly considered it a hot new technology is really what this talk is about. It's about the beast coming back. It's about a very, very old technology that is now coming back. So what we're going to do is we're going to talk about, I'm going to take you all the way back to the beginning of computing. And who can tell me what this is? The difference engine. It's actually not the difference engine. It's a replica of a difference engine. And whose is this? Who's the guy peeking out from behind there?
Babbage, gotta be that.
Yeah, it's Charles Babbage. Right. The reason I have this picture is because this difference engine was used to create things like logarithm tables and things like that. And the data for the table was set in those rods and pins or whatever that is. But information on how to process that was really part of the hardware itself. The software was in the hardware. But this guy, who knows who this is? John von Neumann. And he observed something. He said, you know, computers are designed to process data, and the software that does that processing is itself data. So a computer could, in fact, hold the instructions that it's using to do the processing. And any computer that actually does hold its own data as part, its own instructions as part of its data, is called a von Neumann machine. And essentially all modern computers are von Neumann machines. And because of this, we honor him. Who can recognize what this is? What is this? Well, it's assembly language, right? Does anybody know what the architecture is for this?
6502.
This is 6502. You are way too young to recognize that.
I'm way too old.
All right. So what is this exactly? Well, we call it assembly language, but that's really a misnomer because there is no single assembly language. It's not like C or Python or something like that where there's one language. No, there's really a different assembly language for every architecture of computing, because really what the assembly language is, it's a collection of mnemonics, that represent numbers, because to a modern computer, instructions are really just numbers. But numbers are kind of hard for us to program and to think about, so we have these mnemonics instead. And in fact, this is the way that computing professionals, that systems programmers should write software, is in this assembly language, right? So we get maximum performance for the software, but also have complete control of the machine. Because anything a machine can do, we can tell it to do in assembly language, if it's the correct assembly language for that architecture, right? That's the assumption about assembly. So do we know who these people are?
Ada Lovelace.
And Alan Turing, right. Okay, so these are our systems programmers, and so they're going to write assembly language. But these people, these are scientists, and they're less interested in squeezing the last bit of performance out of the machine, and they may not be interested in getting all of the different options the machine can do. They aren't systems programmers. They're going to write science programs. They're going to want to do scientific programming, and so John Backus invents Fortran for us, right? And specifically for our systems programmers. But what if you're a business programmer? Well, what do you need? What does business programmers want? Well, that's the language, but what are they looking for? Are they looking for the same things that the scientific programmers are looking for? What are they looking for? Scientific programmers are looking for floating point calculations, those kinds of things. What do business programmers look for?
Readability, auditability.
Readability. They tend to look for a lot of text processing kind of things. They look for maybe ease of programming kinds of things. Okay, so yeah, they get COBOL. And who's this come from? Grace Hopper. Grace Hopper's COBOL. Okay, all right. So not only on the software side, but also on the hardware side. Who can identify this hardware? What is this?
Something?
No, this is actually earlier than that. This is a UNIVAC, and this was designed to be it was made for government and businesses. What they said. This is a business machine, right? So this is actually just the control panel, but the rest of the machine is elsewhere. But the point is that this has what a business person might look for in a machine, and it even has something called binary coded decimal. How many of you know what binary coded decimal is? Right? Okay. So the idea is that binary coded decimal is very inefficient. It throws away some of the storage of the machine because we use a decimal digit where a hexadecimal digit would work. But the advantage to that is if you're actually trying to do math at that level, and you're trying to do accounting kind of math, decimal math, then it actually is easier on the programmer, even though it's wasteful for the machine. The machine could store more data. But if you have instructions for them. All right, so that's the business side. It turns out that there's also, this is a scientific machine. This is called a LINC, and it was made for laboratories. And so this didn't have binary coded decimal, but what it has is floating point operation. All right, so we get to the 1960s now, and there's one big particular company that's way out ahead in computing. It's recognized as the computing company. Who would that be? IBM. And IBM released something in the 1960s already ahead, but this particular product locked in its lead and made it indisputably the owner of computing, and that was this machine here, IBM 360. And some of you can see that big red dot. See that big red dot? You know what that is? That's the stop button. Why? Well, because of things like the Foreman project and all these novels in which computers go crazy and take over the world. There had to be a way to stop this thing. And it had to be something that even someone who's never used a computer but has read a novel has to be able to know how to stop this dangerous machine so it doesn't take over the world. And so that was the IBM 360. So I used to work for Boeing. And so I know what 707 stands for. The Boeing 707, first jumbo jet ever made, changed aircraft history, right? And I know what the 707 stands for. Do you know what it stands for?
The sign of 45.
What's that?
The sign of 45, the angle of the wings.
I don't think so. Maybe. No, my understanding is completely some marketer came up and said, "Oh, this sounds sexy." It's kind of James Bondish. It's just a number. It sounds cool, and so that's why I used the 707 and 727 and 737 and everything. So when I first saw the 360, I assumed, oh, it just sounds cool. It doesn't actually have a meaning, but that's not true. The 360 actually had a meaning. What does 360 mean? What was IBM trying to say with this machine? What does the 360 mean? Good for everything. That's right. It is now one new computer fills all your data processing needs. All your data processing needs. That means business and science, right? Country and Western. All of your business processing needs, right? And so that's what the 360 was, 360 degrees. And what that means is that it was designed to be this machine for science and business it did have binary, had hexadecimal floating. It even had decimal BCD. What they essentially did was they said, if this is an instruction you expect on a machine, we will put it here. And BCD is a terrible idea, but business programmers expected to see BCD instructions, so they were there. The instruction set was the most complicated on any machine, and it was actually the first time when the instruction set by itself was actually microcoded. So there was kind of a technological breakthrough there. But this architecture proved so successful. One of the other things they did, and they weren't first to do this, but they also introduced 8-bit byte addressing. This is something we take for granted today. All modern computers are built around the idea that a byte is 8 bits. This is not the way computing always was. Some of the early computers had things like 10-bit bytes, or 9-bit bytes, or 16-bit, or whatever.
12.
6. Now, why would you write a computer where your byte is 36 bits? Why would you do that?
That's on the memory you want to address usually.
That's right, you can cut down on address lines, right? If the most granularity you can approach is 36 bits, then you have fewer address lines for the amount of memory. But there's a trade-off to that, right? The more granularity, the more you're able to use things, and because IBM wanted to support business and do text, they decided 8-bit byte addressing was going to be one of the things they supported. As I said, this is not the first machine to do that. This machine was so successful, it essentially said, this is what everybody's going to do from now. And in fact, it essentially established this C machine architecture a decade before C was even written. This architecture that says each individual byte has its own unique address. Okay? All right. So now we get to the 1970s. Who knows what this is? Who said IBM? You did.
Santa
I
Teresa.
worked there.
You worked there.
In IBM.
That's not IBM. Who said HP? That's not HP. Come on, it's 1970s.
Deck.
Dick.
DEC!
Yeah.
It's also not DEC. Come on, it's 1970s. We're talking about the history of C++.
Oh, well, that's all right.
Bell Labs. This is New Jersey. This is Bell Labs. It's AT&T, right? And so in the 70s, AT&T has the things you need to create Unix. Among the things you need was they had this PDP-8 sitting around. And not this particular one. This is a picture I found. But they had a guy named Ken Thompson who was playing around, and he created this prototype language, and he went and he said, hey, this machine is just sitting around and nobody's really using it. If you give me that machine, I will write an operating system for you to do typesetting. How many of you have used nroff or troff? So nroff and troff were the utilities that Unix was created to do. Because that was the deal. Because AT&T submitted many, many patents, and patents had to be typeset, and they had to pay very expensive typesetting fees. But they had computing power, so Ken Thompson's idea was, hey, suppose you let me make a typesetting application on my new operating system, and all it's going to cost you is letting me use a machine you already have. And so, that's exactly what happened. And we get Unix. So,
That's on my wall in my house.
that's a good thing
That
to have on
license
your wall. Yeah. That particular license plate?
Yeah.
I'm loving that. Great. Okay, so what was Unix written in? What language was Unix written in? C. Excellent. Also wrong. Unix was system software. It was written in assembly language, of course. It wasn't until we get to about release 4 when we realized, look, we want to run this on things other than just PDPs. We want to be able to put this on other machines. And so our choice is, we can rewrite the operating system in a different assembly language for a different platform, or maybe we could do something crazy, like come up with a portable assembly language. Now this doesn't even make sense. A portable assembly language, how could you do that? The whole point of assembly language is to exploit the details of the machine. How could you possibly write a language that could be as powerful and as useful to systems programmers as assembly language, but make it so that it's portable. Well, there you go. Dennis Ritchie comes forward with a portable assembly language. It's a derivation of something that was already in existence called BCD, and then B, and then C. And it was designed to do something that people hadn't done before, which is to do what Fortran and COBOL had done for scientific programmers and business programmers, but do it for system software engineers. And the idea always had been, well, system software engineers don't want that. They want the very fastest. They want to write in assembly language because it's system software. It has to be. Everything else is built on system software. If your system software is slow, your system's slow. Right? You can't recover by some brilliant application programmer writing something really fast on your slow system. Furthermore, systems programmers need to exploit everything on the machine. So they need control over everything, and that's only assembly. But of course, this turned out to be amazingly successful. And we recognize this as this amazing achievement because, what a surprise, it turns out that just like scientific programmers and just like business programmers, system software engineers don't want to have to know the details of every machine for everything they're writing software for. And they need to be able to write code that's portable and easy to understand, and maybe they're willing to trade off a little bit of performance to achieve that. So it turned out to be terrifically successful. Okay, now we're getting to the 1980s. Oh, it's looking so shiny and modern. Now that we've got to the 1980s, now we're going to go back in time. But we're going to go back in time and talk about these guys. Anybody recognize these guys? You can read their name, but do you recognize them? Who knows who these guys are? So this is Dahl and Nygaard. This is Kirsten and Nygaard. What did they do? Pascal. No, but that's a good guess.
Object orientation.
They did Simula. They did object-oriented. They got a Turing Award for ideas fundamental to the emergence of object-oriented programming through their design of the programming language Simula 1 and Simula 67. But it turns out that Kirsten Nygaard is actually a professor at this small town in Denmark that happens to be the hometown of the hero of this presentation, which is Bjarne Stroustrup. So Bjarne does his graduate work at the same university where Kirsten Nygaard is as professor, and of course Kirsten Nygaard teaches him all about how you do simulations, how you do object-oriented programming using Simula. So Bjarne goes off to Churchill College in Oxford, and he's working on his PhD, and he decides that as part of his PhD, he's going to do a network simulation. He's going to simulate how a network would behave. And it's a simulation. It's perfect. What's he going to use? He used Simula. That's what he was trained to do, right? You're going to do a simulation. You want to do object-oriented programming. You do this in Simula. So he writes his application to do this simulation of the network to get testing, and he runs it on the Churchill College computer for a while, just until the computer melts down. The administrators come in and terminate his application because the simulation just overran the abilities of the computer and nothing else was happening, and it didn't work. So I'm going to break a huge rule of presentations. I'm now going to read you a couple of screens worth of text, but it's because I think this is so important to C++. Because what Bjarne said is, so I rewrote my simulator from Simula into BCPL. Remember, this was his predecessor of C. And all of the high-level structure disappeared. All of the nice organization that had helped me debug and helped me design disappeared. But the resulting BCPL, once I debugged it and lost half my hair in the process, ran really fast. It could use all of the resources of the machine. It could communicate with anything on the machine, and I got my data, and I got my PhD. I came away with the opinion that I would never again want to attack a problem with tools that were fundamentally unsuitable. And in particular, I don't want to make the choice between elegant, which Simula was for this problem, and efficient, which BCPL was. I want both. And that has been sort of one of my guiding lights. If you give people the choice of writing good code or fast code, there's something wrong. Good code should be fast. So Bjarne gets his PhD, and he gets hired at Bell Labs, And he decides, you know, Bell Labs, of course, everything's in C because that's where C came from. And he decides, you know what? I would like to build extensions on C that allow me to do this simulation stuff. I want higher level abstractions built into the language than what C has. C is portable assembler. C is great for system software. C is not great for high level abstractions and very large applications, things trying to do simulations. But maybe we could extend C to do that, keeping the low level control, the high level, the low level control and the high performance, but at the same time adding in the extensions that let us do the kinds of things that we can do in Simulink. So he started working on something in the late 70s called C with classes. It became C++, got renamed as C++. And during the 1980s, I'm not quite to the 80s yet, we started doubling the number of users every 7.5 months. So we're going to stop the progression now and say, why C++? Why would people do this? Well, it's because we get these high-level abstractions at low cost. There's low abstraction cost. We have low-level access when you need it. You have a wide range of applicability, highly portable, better resource management. Now, I'm not going to go through all of these things, but I want to hit some high-level things. And one of them is high-level abstractions. And I've got a whole list of these abstractions, but all of these things are provided to C++ programmers with very low abstraction penalty, very low overhead, zero overhead. So let's talk about user-defined types. And the reason I want to focus on this specific one is because in C++, the way we solve any problem is by defining a new type. That's just what we do. We declare some new type. That's how we solve problems. So with our user-defined types, they have to have the power and expressiveness of built-in types. Having operator overloads, not all languages support because some people are worried that it's going to be confusing for users. Yes, but it also allows us to write a library with a great deal of expressiveness. Almost anything that can be done with a fundamental type can also be done with a user-defined type. That is a flexibility, that is a design paradigm that most other languages just can't touch. For example, a programmer can define a type that functions as a fundamental arithmetic type. If you look in the standard library, there's something there called complex. Complex numbers, what is that? That's the a number that's made up of both a real and an imaginary part, right? And this is a really important thing for certain areas of science. And I've never heard anybody suggest that we need to build this into the compiler and make it part of the language. It's just part of the library. But the reason nobody has suggested doing that is because there's no particular reason to believe that it would be any faster built into the language than it is in the library. That's the power of what you can do with the library. You can make things that are as efficient as the fundamental types and has the same API as what you expect for the fundamental type. You want to add two complex numbers? What do you use? Use the plus sign. Why? Because that's what people expect to add numbers. That is the power of what you can do. You can also have object pointers emulated. You can write your own type that works like an object pointer or works like a function pointer. And in fact, due to some remarkable properties of inlining, it is actually possible that if you make a function object, it's actually more efficient than a function pointer because of its ability to do inlining in generic elements. This is a key property of C++, the fact that you can design your own type that has this kind of expressiveness, this kind of power, this kind of efficiency. Absolutely critical to its long-term success. There are all these different high-level abstractions that are supported at low cost, but they are not forced on you. Right? If you want to write an object-oriented style, C++ supports that very well. If you think that object-oriented styles are awful and you don't want to have anything to do with it, you can write in procedural style or generic programming or whatever you want. It's like a Swiss Army knife. These things can be added and used, intermixed as you choose. It's up to you to decide what kind of paradigms you want to use. Mixing free. I think of C++ as a language for creating libraries. That's what I think it is. And I think of it that way because of the fact that you can do so much with a library. You can make a library that has incredible power, efficiency, safety, that's natural syntax because of our ability to overload operators. You can make type-specific optimizations. We can write something that's general, but if you have a particular type, we can specialize the generality with a template specialization and take advantage of type-specific things. Automatic resource management, because we have deterministic destruction. All these kinds of things allow us to build libraries that do amazingly powerful things, but have usable APIs. Potentially usable APIs. All right. So this is based with little or no abstraction penalty. So Bjarne refers to this as the zero overhead principle. Now, some people misunderstand what exactly the zero overhead principle means. Some of these features literally have no overhead, but that's not the zero overhead principle. The zero overhead principle says it has no overhead at all, or if it does have overhead, that overhead is no greater than what you would have if you wrote the feature yourself by hand from scratch. Right? It is as minimal, right? If you don't use the feature, you pay nothing. If you do use it, you pay no more than if you coded it by hand. That is the zero overhead principle. It's not that there's no overhead. It's that there's no abstraction penalty. You're not paying any more than you would pay if you wrote it by hand. And in fact, in the early days of C++, and I've been programming in C++ long enough to know that it used to be, today people think of C++, yeah, it's really complicated stuff, but it's really fast. But in the early days of C++, it was, no, it's really slow. You know what happens when you call a function? It does this extra indirection to get that function. Oh, it's terrible. That what overhead there is, right? Because compared to C, C++ had more overhead. But if you look at people writing C, very often they basically reinvented virtual functions because that's the paradigm they were trying to accomplish, and they wrote it themselves. And generally speaking, it was less efficient than what do you get in C++ when it's built into the language. We also have low-level access. Notice that this all comes free to us because C++ was built on C, and C is portable assembly. Anything you can do in this portable assembler, you can do in C++ because all that stuff is just available free. We get it free by buying into the baggage that we get with C, which didn't have necessarily the perfect declaration syntax, and it has some baggage. But by buying into that and accepting that, we got all of this kind of benefit from a proven language with all these features. One of the things I want to talk about is management of how you make a user-defined type. So most languages, object-oriented languages, somehow allow you to create an object, you allocate the memory, and then you run some kind of construction function. In C++, we call it a constructor, but other languages have different terminology. But basically, it means I need to go to a heap, create some memory, and then make it, clean it up, make it ready to be an object. For most languages, that is done only on the heap. But in C++, you can construct that not just on the heap, not just in static memory, not just on the stack, but you literally can take any arbitrary memory and do an in-place new and create an object right here on this memory. And I will control its lifetime, I will decide when it's destroyed, and then I can free the buffer up. That is a level of control way, way beyond what most object-oriented languages give us, but it is what we expect in C++. We expect to be able to have that kind of control. We expect, gosh, I've got a vector here, I want to put objects in it, so I'm going to arbitrarily create objects at any point in the vector and individually control their lifetimes. One of the things that we can do, because we have this kind of control, is we can do things like worrying about cache optimization. Cache optimization is a very important feature. It's something that we are very, very concerned about now, which maybe 20 years ago we didn't think too much about cache, but now it's all about the cache, right? And a lot of languages don't have to worry about cache optimization. It's not because the language is so good at providing cache optimization for you, it's because it just doesn't give you any tools that you can do anything about it. It's either cache friendly or it's not, and you have no say. Whereas in C++, you can decide how things are laid out in memory. If you want to create a user-defined container that you think is going to do a better exploit of caches, you can do that. The built-in containers like arrays, vectors, and decks do very good, are very cache-friendly. All right. One of the philosophies of C++ is we don't want to solve the specific problem, we want to solve the general problem. We want to be able to scale. And we want to be able to scale because as software engineers, that's the question we always ask, right? I mean, if I come to you and I say, hey, look, I've got this thing and it does a cool thing. As a software engineer, the question you're going to ask is, yeah, but does it scale? Can we do that at scale? And we want to be able to scale up, but we also want to be able to scale down. We don't want to have a lot of overhead. Is it possible to make a low-level driver that doesn't take much memory with this language? So we want to be able to do things at the low end, embedded devices, all sorts of things, maybe CGIs. We want to say you only pay for what you use. So if you are asking only to do a very small thing, we don't want a lot of overhead force on us. We want to be able to live in a low memory footprint. But at the other end, we want to be able to scale to high end. Part of it is not just necessarily the applications itself, but the process of developing. And one of the decisions made about C++ is that we do separate compiles and then link them together. So that allows to be able to support really, really large teams with scores and scores of modules because of this separate module compilation. All right. It's very highly portable because, of course, it's based on the C machine model. So we're going to talk a little bit more about Alex Stepanov later, but I remember he was on a panel once, and he happened to make the observation, and he said the only languages worth studying, of course Alex might be a victim of a little bit of hyperbole, but he said the only languages worth studying are C and C++ because they're the only ones that in the language model the machine model. The creators of the language weren't trying to make some mythical machine that worked the way we'd like it to work and then create a runtime that kind of modeled that. No. The C and C++ look at how machines are actually built and build and implement the machine model, the C machine model. Of course, there's a bit of an incestuous thing because the success of C and C++ have meant that hardware builders are trying to implement that particular model, but that's the situation we're in, right? Because we're not trying to make some kind of virtual machine that has wonderful features. Instead, we're simply trying to model the model that machines are actually built. It means that the requirements to make a C++ runtime on a given platform are minimal, and it's very easily to port this to a number of different things. Almost any platform you look at has one or more C++ tool chains. Often, C++ is the only high-level language alternative that's available. In fact, on all of the top mobile platforms, C++ is the only high-level alternative that's available on all those platforms. And then C++ can be written to support all these platforms without rewriting. You can write portable code. If you want to take advantage of particulars on a machine, you can write code that's not portable. But you have the option of achieving what you need to do in a portable way for most users. All right, so let's talk about the fact that because things are highly portable, we have a huge amount of infrastructure dependent on C++. This is the history of C++. And that is that we have all sorts of factors outside the language itself. Suppose I came to you and said, hey, I've got this great new language. It's got a wonderful syntax that is just as smooth as butter. It's great to program it. It's just going to be a joy to program. You get excited. You say, okay, let's use that for our next project. It's like, well, yeah, sure. Of course, we can't hire anybody to ever use this language because it's a brand new language. We can't watch any videos on YouTube. We don't have any real tools for it. There's no good infrastructure support. We can't port it to other platforms because it's a brand new language, right? The challenge for new languages, and there are literally thousands of languages, the challenge is not to write a better language than C++. I'm going to do that for you before your very eyes. You ready? I'm going to create a new language that is better than C++. I guarantee you're all going to agree that this new language is better than C++. Here's my new language. It is exactly like C++, except no specialization for vector bool. It's better than C++. Now all I have to do is get 5 million users and bye-bye Bjarne. right? Okay, the challenge is not to make a better language. The challenge is to get this level of industry support that we can get from C++. So this is one of the things, people ask me all the time because of what I do. Well, what about this language? What about this up-and-coming language? It's really exciting, does some stuff that's great stuff. I'm not going to make the contention that C++ will always be the biggest language. My contention about the value proposition of C++ is that it's a unique combination. It has low-level performance. Lots and lots of languages just don't have that. If you're trying to do low-level memory layouts in Python, you're looking at the wrong approach, right? So C++ has that, but other languages also can be used for system software, like, of course, C. But C++ also does high-level support, high-level abstractions. We can do things in it, making very, very large applications with very high-level abstractions. C doesn't give us that, but lots of other languages do. And in fact, there are recent system software languages that are designed to do both of those things. They do give us object-oriented and other high-level support, but they are capable of low-level system software. But what they don't have that is unique to C++ is they don't have this kind of industry support. The three of these things together is unique for C++. There are languages that even have better industry support than C++ does, maybe Java, or maybe Python, probably not Python, but there are other very popular languages, but they don't give you the other two things. There are also other system software languages, but they don't give you both of the other two things. And there are lots of high-level support languages, but they don't give you both of the other two things. C++ is the only thing that gives you all three of those things. That's the unique value proposition of C++. And it comes from the fact that we have this large installed base. Right? Okay. I want to talk about one feature, and that's resource management. A very, very common approach to resource management is to have a built-in automatic garbage collection. Most languages go that way. C++ doesn't. But it's actually a good solution to a really, really bad problem. Now, in this lighting, some of you might not notice, I have one or two gray hairs. Each one of these gray hairs, that's a memory leak. Right? I have a great deal of appreciation for any solution to the memory leak problem. I've been up way too late, way too many times working on memory leak problems. If you can solve a memory leak problem, I'm for it. And garbage collection is a solution. But it's an engineering solution. That means that there are trade-offs. It's really good about some things. It's easy to use, but it has some trade-offs. It's not necessarily the kind of thing that we would want for C++. For one thing is, memory may not be released until an unspecified time. That's maybe not such a big deal for memory, but if you're trying to track other things other than memory, for example, let's say we have an object that one of its data members is an open file. We have a file handle as one of our data members. If that object doesn't get disposed of in a timely manner, we are holding that file open, and that might be a problem maybe for our own app, also trying to open that file in another context, or some other app. So not being able to release memory, even perhaps not at all, because some garbage collectors, of course, it makes sense. If you don't actually need that memory ever, then why release it? But when it does release memory, sometimes it's not under control of the program. It leads to a situation where you're using an application that has garbage collecting, and all of a sudden it freezes momentarily while there's a bunch of garbage collection going on in the background. A lot of applications or languages that have garbage collection don't allow you to say, I have a critical window here, don't do any garbage collection for this window. It's usually not available, all right? And in some cases it requires a large buffer of unused memory. I'm not an expert on this, but I've been told that one of the issues for Android apps is that you have to have a lot more memory than what they actually use because of the way the garbage collection system works. All right. So in C++, we've got to have a better solution, and one thing is we need to generalize this. Memory is not our only resource. We want to be able to handle, as I said, file handles or other operating system resources, and we want to be able to handle them in a way that as soon as we're finished with it, we can release it. And that release should happen immediately. We would like to have a feature of C++ called Deterministic Destruction. That is that when an object is no longer in use, It's deterministically destroyed. Deterministic means that it's not at some arbitrary future time, and in fact, looking at code, we can examine exactly when individual objects will be freed up and exactly what order they will be freed up. This is incredibly important. There is a programming idiom in C++ called RAII. It's a terrible acronym as it is. It's usually interpreted as resource acquisition as initialization. I think that's a poor interpretation. We should call it responsibility access. Responsibility acquisition as initialization. Why do I like this term? Well, because I think that resource doesn't include everything we want to talk about, but it also includes things we don't want to talk about. One of the most valuable resources that we have in our language is we can get the current time. There's things that we can do because we can get the current time. There's certain apps we couldn't write if we could do it. It's a very valuable resource. But getting the current time doesn't require that we initialize an object or manage it. You know, if we don't put the time back, it doesn't, you know, we're not time lords, we don't have time slips or, you know, something like, no, we don't need to do that. So it's a resource, but we don't need to manage it in that sense. The other problem is that there are things that are not resources that we do need to manage. So imagine I'm working on a GUI application and I would like to draw my object. I've got an object, draw method comes in, I need to draw my object. In order to draw my object, I need to change the foreground color. I now have to restore the foreground color, or the next object being drawn is in for a nasty surprise. But changing the foreground color, that's not really a resource. But it is a responsibility. And so that's why I say that RAI objects are not really for managing resources, they're for managing responsibilities. As soon as I do something that I have to undo, as soon as I make a database connection that I have to release, as soon as I open a file that I have to close, as soon as I allocate memory that I have to free, all of those things are responsibilities. Getting the current time, that doesn't incur a responsibility. It's a resource. Knowing the current time is a valuable resource, but I don't have to restore that anymore. So I prefer this, but regardless of what we want to call it, the point is that this approach allows us to do a better job, more control than what we do with garbage collection. Gives us more control. We don't have a situation where the system, without any say from us, is going to freeze while we collect garbage or anything like that. It does require a little bit of support on our side. We have to follow the discipline of using RAI objects, but those RAI objects are user-defined types, and C++ is very good at making those kinds of user-defined types. The other thing I want to touch on very quickly is that the finally keyword, which a lot of languages use, actually violates DRY. Who can tell me what DRY is?
Don't repeat yourself.
Can you say that again?
Don't repeat yourself.
I'm sorry, one more time.
Don't repeat yourself.
One more time.
Do not repeat yourself.
Thank you very much. Thank you very much. All right. The idea here is that in C++, like in any other language, when you use resources, we need to clean those resources up. The approach of using RAII means that the burden of doing that cleanup is in the library, not on the user. If every time I use something, I have to write a finally to clean it up, that means I'm writing I'm writing this code in lots and lots of places. I use something, I have to clean it up. No, I want to create an object that's part of the library that says, oh, if you want to use this, here's how you use it, and when it goes out of scope, it cleans itself up. And that is the C++ way. Okay. All right. Have you ever noticed that Michael's Case's name doesn't come up often enough in talks? You ever notice that? Oh. So now we get to the 1990s. The big thing about the 1990s was object-oriented programming. I lived through the 90s. That was the big hype. Object-oriented programming. It was a strongly hyped paradigm. But one of the things about it was that C++ was seen as the object-oriented programming language. So during the 80s, the number of users was doubling every 7 months, and then during the 90s, it was all about the object-oriented programming, and people were trying to master C++ to master object-oriented programming. Now, you probably get from my tone that I'm not a huge fan of object-oriented programming, but I would say there's one type of programming that maps very well to object-oriented programming, and that's GUI, developing GUIs. GUIs work pretty well in the object-oriented approach. And it turns out the 1990s was kind of the battleground between Mac and Windows. Everybody was trying to do GUIs. And C++ was a great way of doing it. So C++ became more and more prominent in the 1990s, gaining more and more influence. In fact, it was during the 1990s that a number of large companies that had invested heavily in C++ approached the creator of C++, Bjarne Stroustrup, and said, we think it's not great for the C++ community to have C++ in the hands of some professor from New Jersey. We would like to have an international organization defining what C++ is. So Bjarne agreed to this and has been active in the ISO Standards Committee for C++ for many years. So it was also during the 90s that this individual was working on a project that wasn't object-oriented programming. This is Alex Stepanoff, and he is not a fan of object-oriented programming. He was going his own way. He was working on generic programming. And he was working on a library where the approach was to be able to implement algorithms only once. Let's write the algorithm one time and figure out how to use that same algorithm no matter what data we're trying to operate on, no matter what the container that we're trying to operate on. Let's reuse this, write the algorithm once, capture the essence of that algorithm and do it once. It's phenomenal to think how few people hadn't thought about this before. It's just amazing to me. It seems such a natural thing in retrospect. Why weren't we all doing that? And it turns out that this approach has actually been done in two languages. So both C++ and D have an implementation of this approach, but both of the languages essentially had to be rewritten to support it. It seems like such a natural thing to want to do, and yet there's no language on earth that could do it without being modified. So what happened here is that this fellow here, his name's Andrew Koenig. He had worked at Bell Labs, and so did Alex. And so he sent an email to Alex, and he said, we're working on the standard library for the new release of the C++ standard. And he said, are you thinking about submitting your generic algorithm library to the standard to be part of the standard library? And Alex said, oh, no, not doing that. He said, first of all, it's way larger than anything the Standards Committee has looked at before. The little tiny things that they're looking at, like the string library and the stream library, they're dwarfed by what I'm doing. It's going to be way bigger than what they're used to. But the other thing is, they're also not going to get it. And I appreciate why he says that, because I was programming in the 1990s, and when I first saw this library, I didn't understand, what? Because I was used to working with container libraries. I was a contractor in the 1990s doing C++. So I would go from project to project. I'd work 9 months or 12 months on a project, then go to another project, and I had to relearn all the container libraries, because every framework had their own container library. So I was excited about the idea that there's a container library that's designed to be, the ultimate container library. If it's in the standard, it's going to be available everywhere. Great, I learned one library, I can use it. So I started to work on it, started to learn it. And it's like, what? This is so different than everything else. So wind your brain back to the 1990s, this world where everything is object-oriented. What is a container in that world, in an object-oriented world? We're not using value semantics. When we say we put something in a container, what we mean is we pass the pointer into the container, and the container now is responsible for deleting the object. You've just put the object in the container. The first time I put an object in a vector, I said, wait a minute, I didn't put an object, the object is still here. I made a copy of it and put that in the vector. Because I wasn't thinking in terms of value semantics, I was thinking in an object-oriented way. That's not the way that Alex was thinking. But Alex had demonstrated his library and explained it to many, many people. And they all had the same response that I did, which is, what? And so he knew that that's what the Standards Committee was going to do. So Andrew wrote back and said, Alex, I agree with you. The Standards Committee is not going to accept your library if you don't submit it. So Alex understood what he needed to do. He and his team went without sleep for several weeks while they pulled together a formal proposal to give to the Standards Committee. And by the way, what he did when he shipped this off, he actually went to the Standards Committee. I've talked to Alex about this. He hated going to the Standards Committee, but he went once. He gave a lecture explaining what the library was about. And in fact, he was right. First response of the Standards Committee was, whoa, this is way too big, and what the heck is it? They said, it is our mandate to standardize existing practice. This is a research library. The number of people actually using it in real work is trivial. This is not existing practice. But, as they discussed it, as they debated it, I have to give them a lot of credit because they reached an understanding that I didn't. Of course, they had the advantage that Alex had explained it to them for an hour and a half, which I didn't have that advantage. But they did get it. They got it, and they said this has to be part of the standard. It turns out that there's actually the name for this, which is the Standard Template Library. But that is not the name the Standards Committee gave. That's the name that Alex slapped on it when he submitted it. If you think about it, it's a little presumptuous because it wasn't in the standard at the time. But that's why sometimes people argue over what exactly is in the STL and what's not. Because the STL name went on the original proposal, only some of which was accepted. Some of which the Standards Committee said, no, we're not going to do that, we'll do it later. And some of those parts went into Boost, and then they came back into the standard library later. So when you talk about the STL, what do you mean? Do you mean just the original proposal as it was proposed? Do you mean the original proposal as it was accepted? Do you mean what was accepted, but what was part of the proposal and then came back? There's a million ways of interpreting it. My interpretation is that the STL is actually a set of conventions. It's not a set of containers or even a set of algorithms. It's a set of conventions. It's a way of writing it. So from my point of view, if you're writing an algorithm on your machine, even if it has never seen the Standards Committee, I consider your algorithm part of the STL if you follow these conventions. Because that's what the STL is to me. It's a set of conventions about how to write generic algorithms. Okay? All right. So, when the standard shipped in 1998, this is Beeman Dawes. He was the chair of the library subcommittee when the standard shipped. And he had been very much involved in this acceptance of the STL. But he was also concerned about something else, which is the mandate of the committee. They'd shipped one standard, but of course they weren't going to go out of business. They were going to try to improve the language and expand the library. But the mandate of the Standards Committee is to standardize existing practice. Now they violated that by accepting the STL because that was a research project that didn't have much usage. But the mandate was standardize existing practice. And there were some libraries that were widely used, but they were all proprietary libraries. So that's what you had. You had libraries that were open, that could be submitted, but they weren't widely used. And you had proprietary libraries that were widely used, but couldn't be a candidate for standardization. So he took this problem very seriously. And what he did was, he and some other people in the standard, on the Standards Committee, people in the library subcommittee, decided what we really need is a way to encourage people to write libraries that can be given away freely, but are of high quality, so that they're candidates for being included in the standard. So he, Dave Abrahams, and other people created Boost, with the idea that this was a place that libraries that are open source, freely available to everyone, no restrictions on their usage, no restrictions even on modifying them, and in fact you don't even need to say on the outside of your application, you know, Boost libraries used in this. No, it's the freest open source license there is, because it doesn't require any acknowledgement at all on the finished product. And they said, but you can't just, we're not just going to take your library that you've worked on and you dump. No, it's going to be peer reviewed. It has to be of high quality. And the idea was that these libraries would be candidates to go into the standard, and even if they never made it to the standard, if they're widely used, that's a benefit by itself. And in fact, by any stretch of the imagination, Boost has been wonderfully successful. Almost everything that's gone into the library since the original release in 1998, when Boost was formed, has been either directly from Boost or strongly influenced by what we've learned at Boost. So it's been incredibly successful. So what do we have? We have a language whose users have been doubling in the 1980s at the rate of every 7 months. A language, that was so popular and so dominant in the 1990s that was the highly hyped highly hyped paradigm of object-oriented programming, and it was just seen as the language. It became an international standard in the 1990s, and we saw one of the most successful open source, very early open source projects in the world. This is a language that's going to dominate the entire universe until we get to the 2000s. And then this happened. So just when it looked like C++ was really, really raring, we ended up looking at Java. And Java also supported object-oriented programming. And he did it in a way that might actually be a little easier to use. You don't have to deal with all those, operators and all that kind of stuff. And it's the language of the web, whatever that means. But it sounds like, that means it's the language of the future, right? And it's almost as fast. And you have to understand something that was happening in the 2000s. In the 2000s, we were in this interesting situation where the processors were so powerful. Our desktop machines had so much computing power that the operating systems at the time had to have a bunch of gratuitous animation in order to justify you buying more hardware, right? You just didn't need to worry about performance anymore. Performance was something for the 20th century. The 21st century, the machines were just so powerful, the performance was no longer an issue. So why use a language that has baggage and is hard to program in like C++ when you can use a language that's wonderful to program like Java, and it's almost as fast on machines where we don't care about performance anyway because the machines are so fast, right? Say right. Give me this one.
Right.
It's also easier to learn and teach. You can almost imagine some college professor back in the 2000s calling the head of the department and saying, our object-oriented programming class that we have, yeah, the one where we teach in C++, yeah, just think about if we were to teach that in Java instead, we wouldn't have to teach pointers. We could skip all of chapter 9, right? And that's what happened. A lot of universities switched from teaching Java or teaching C++ to teaching Java. All right, so let's talk about this almost as fast thing. This, as I said, the desktop computing in the 2000s was so powerful that it seemed like, well, maybe we just solved the performance problem in computers. Now they will just be fast enough that we no longer need to think about high-performance software. We can think instead about software that's easier to program. And it turns out, with C++, you get a lot of baggage. You get the C syntax baggage. You get a lot of complexity, like templates and generic programming, operator. And did I mention pointers? Pointers are hard, right? And C++, all about these pointers. And it turns out these managed languages were fast enough. So there's actually two virtual machines. There's the Java virtual machine, Microsoft's common language, and colleges decided maybe teaching these things. Did I mention pointers are hard? I did mention that point, right? I made that. Okay. All right. Something else happened, and that is, remember the standard at the end of the 90s ships in 1998. Standard ships in 1998. Now, something interesting happened at the Standards Committee after it shipped. Now, think about this. We are used to a world in which, when a standard comes out, there are implementations that implement that standard very, very soon. When C++ 11 came out, we had two implementations that had pretty much implemented it by 2012. When C++ 14 came out, we had a couple of implementations that implemented it in 2014, right? And in fact, as features come into the language, very often they're implemented before they're actually standardized. The committee says, we decided we like this feature, and the people on the committee, who happen to be the compiler writers and the library creators, they run home and implement those features, and those features are actually in users' hands before the standard formally ships. That's the world today. But the world in 1998 was, and I was there, I remember when the standard shipped, and I was excited to use it, But I was told, and this was not controversial, everybody agreed that it would be 4 or 5 years before the standard, the 98 standard, would be implemented by any tool vendor. So that puts the standards committee in an awkward position. They would love to start standardizing more features, but they couldn't get any feedback. They got feedback from implementers, because the implementers were starting to implement these features. But they couldn't get any feedback from users, because the users weren't going to get to try these features. And so the standards committee itself put itself in bug fix mode. In other words, the next release of the standard, which would come out in 2003, added no new features at all. It was bug fixes, but not bug fixes of software, bug fixes of the standard. So what does that mean? What are they fixing? Terminology, contradictions, ambiguity, things where, because of the way it was worded, it wasn't actually implementable, where the wording probably didn't match the intention. Those kinds of things got addressed. So that in 2003, we sent out another standard, and it was about 2003 when we started to have results from users of real-world experience with the standard, and they started to actually standardize new features. But what happened then in 1998 is the standards organization ships the 1998 standard and goes in bug fix mode. And what happens to the committee itself? It got small. Why? Because who wants to be in bug fix mode? Right? Attending the standards committee, you don't get paid for that. You have to beg your boss to send you to the standards committee so that you can do work for free. And if all you're doing is bug fix mode, you're not adding any new features, that's not so interesting. So the committee got small. So on top of all the other things that was going on with Java, we also had a situation where the committee didn't actually even start adding new features until about 2003. And when they did that, they made a list and said, when all these features are standardized, we'll ship the next standard. And this was a mistake, because now we've changed this, and now we try to release a standard every 3 years. But at the time, it made sense to say, when these features are all there, what do we want? Well, we want lambdas, we want multi-threading, we want all these things. When we have all those things, we'll ship a standard. And that'll take probably 3-4 years. And it turned out that it was a total of 13 years. There was no major release from the standards committee in all of the 2000s. So this is the problem. A language that looked like it was just about to explode and own the universe instead hits this thing called Java, and it becomes not the exciting thing to do. The standards committee, although they were actually busy during that time, when C++ 11 finally ships, it has lots of new features. They weren't wasting their time, but they also weren't shipping anything. So C++ lost its momentum. C++ lost its glamour, and suddenly Java was the language of the future. But something then interesting happened with the 20-teens. Part of it was the release of C++ 11, but there was actually some other factors, and we're going to talk about that. But what happened is the beast started roaring back. So notice that we thought we had solved the performance problem, and perhaps on desktop computers we have, but desktop computers are not computers anymore. What's a computer? A computer is, where do I leave my computer? A computer is something you put in your pocket now. And it turns out that even if your pocket computer is fast, that's not good enough. You still want the best possible performance. Why? Because you don't want to drain the battery. Right? Performance still matters. We thought performance wasn't going to matter anymore. We have these incredibly fast processors, and computers are just as fast as they need to be. How fast do you have to blink the cursor in a word processor? It's as fast as it needs to be. But it turns out, no. The world doesn't end on the desktop. More and more computing power, and we want to have it here. We want to think about, that battery performance. We want to think about maybe less expensive processors. And then here, there's probably no battery there, but we want to think about performance per dollar of hardware, performance per watt of power, performance per watt of cooling. That means performance is important. And using a language that's almost as fast may not be the choice you want to make. So there's a fellow named James Hamilton. He works for Amazon, and he did this study of what he called modern high-scale data centers. And what he means by modern high-scale is, assume this is a data center where the entire data center is essentially running the same piece of software. Maybe different parts of a larger system. But it's not a data center like your university data center where thousands of people are submitting different jobs. No, this is something where you have thousands and thousands of machines that are doing mapping, or thousands and thousands of machines that are doing a search engine. Okay? So that's what he was looking at. Weather forecasting, whatever it is. It's a single piece of software that's distributed over thousands of machines. And what he found out was that in decreasing costs, the cost is hardware, and then power distribution and cooling. We actually spend more money cooling them down than powering them. And then network equipment, also part of the hardware, and then other infrastructure. Notice the interesting thing here, that the top three are all directly related to software performance. If you can make your software 10% more efficient, then, sorry about that. If you can make your software 10% more efficient, then your total costs drop by 9%. It hits that part. What were you saying?
Oh, I was just going to point out that if you have a $100 million data center and you can make the software on it run 1% faster, that's worth $1 million, and that's why programmers who can do that get paid a lot.
Yeah, but notice, here's the interesting thing. Where is the salaries of the programmers and the IT professionals? That didn't even show up. That's in this other infrastructure stuff. It turns out that if you were designing your language to make it easier for programmers so that the programmer would be more productive, you put your money in the wrong place. We don't want the programmers to be more productive, we want the software to be more efficient. That's the sweet spot, right? So, yeah, it's in the noise. Managed code optimized for the wrong thing. Instead of optimizing for performance, get optimized to make it easier for programmers. All right, so we shipped 2011. Yay! All right, what happened then? Well, we know what happened when we shipped 1998. What happened to the committee? Shrank. What happened in 2011? Well, we created a language that felt like a new language. This is a quote from Bjarne. Feels like a new language. So much more power, so many more ways of doing things, so much easier to do certain kinds of fundamental template kinds of programming. It seemed like a new language. And what happened is the page count, it essentially doubled the language. That's why it seemed like it was new. Now, one of the problems with C++, one of the challenges it has, in fact, if you ask a bunch of people who know about C++, what's the biggest challenge in C++, what's the biggest problem, almost all of them would say something along the lines of complexity. It's just too complicated a language. How many of you have ever said to yourself, boy, C++ would be so much more of a joy to use if it was just a little bit more complicated? How many of you can say that? All right. All right. So the problem is, if you try to simplify the language by ripping out features, and there's lots of things that are features that we would like to have gone, like vector bool, right? There's lots of things that we'd be happy to get rid of, but what happens if you get rid of them? You break your code. So just think about, I don't know what companies you guys are in, but think about the value of your C++ code that your company owns. What's the value of that code to your company? Now multiply that by all the companies in the world, and you see that C++ code represents literally trillions of dollars worth of value. And if the committee comes along and says, well, you know, we've made this little change and now all your existing code won't compile, well, you just subtracted value from the universe on a huge, huge scale. So the committee does want to simplify, but it turns out that you can simplify by adding. And that's something that seems weird. It does actually create more page counts, but things like auto or range-based for loops, or being able to say in a template declaration, a nested template declaration, enums being more consistent, uniform initialization, all of these things are designed to make things simpler, even though they're actually adding things. But there were other things done in the language too. For example, things make it more modern, like lambda expressions, improving support for Unicode, a number of things moving into the standard from libraries that people expected, like tuple support and smart pointers. Right? And then there's even some things that, that were specifically targeted at library authors. So maybe users say, well, these things aren't really interesting for me. What do I want variadic templates for, or perfect forwarding? I don't even know what that is. But the truth is, remember, C++ is about making libraries. If the library authors have better tools, you have better libraries. Okay? So that's what that's about. And then new areas, like, for example, multi-threading, which has never existed before. Well, never mind, it's good. But move semantics, which again, other languages don't think about move semantics because other languages don't have that level of control. So this is what's going on when we ship this language. Who knows what this is? Well, it's the LLVM logo. And it turns out that Clang didn't suddenly appear in 2010, but it seems like it because before 2010, the C++ compiler in Clang, there was a C compiler, worked great, had lots of cool features, but the C++ compiler wasn't quite there yet. They were scrambling to add features as fast as they could. And it was about 2010 that it suddenly, I should say suddenly again, but it seemed like suddenly it was usable. And one of the things it did was it created competition, because even if there weren't a lot of users that immediately were switching to it, there were a lot of users that were looking at demos and saying, you know, our error messages could be a lot better. If you don't think about that, go back to a version of your compiler from 2010. Your compiler's not Clang, and look at the error messages you get and see how much better they are. And build performance. So, you know, generating optimal code, really, really hard to do. So the initial performance edge for Clang was not really in building the best performing code, it was doing so much better in the build itself, build performance. These were the things that drove the other compilers to be more competitive. But something else, and that is that Clang is not really a compiler. Clang is really a toolkit. It's designed to have a number of things that can be put together to be a compiler. There's a lexer, and there's all these different components, which you can also make different kinds of tools out of, like sanitizers, or add new kinds of features just to test out language features. And it was designed to be able to do that. Now there's another open source compiler, but it was actually specifically designed to not be able to do those kinds of things. It was designed to make those kinds of things challenging, because that was a non-goal for that compiler. But for Clang, the entire goal was to be able to make a set of tools that could generate, it could be used as a compiler, but also be used to make a number of different kinds of tools. And I think in the long term, this is the bigger impact, rather than as a compiler and competitor there. The other thing is that open source really, really works to C++'s advantage. And open source has become much more important since 2010. It turns out that the compiler can do lots of cool things if it actually sees the source, particularly when we're talking about template stuff. And so open source libraries are really C++ friendly. You can see, in fact, that on GitHub, which is not really a C++ friendly site, it's more all about web languages, but you do see that about this time, C++ becomes relatively more popular on GitHub. And then we get back to the International Standards Organization. When we saw it in 1998 and we shipped a standard then, the committee got smaller. But when we shipped the standard in C++ 11 timeframe, because there was excitement about all these new features and because tools were implementing those features so quickly, the reverse happened. And in fact, what happened was a whole bunch of new subcommittees were created to deal with the fact that there were lots and lots of people who got excited and said, wait a minute, C++ can change? I thought C++ was like Latin. I thought it was a dead language. We use it because it doesn't change. Well, it turns out when C++ 11 comes out, it's all these new features, we suddenly realize I could go to the standards committee and I could create features that humans would actually use. And so a whole bunch of new study groups were created to work with these people. And actually, this is a very dated slide. We've actually added 2 major new committees and a bunch of new study groups. I think the study groups are now up to 17 or 18, do we know? And now we have something called Evolution Incubator and Library Evolution Incubator. So there's 2 more groups here because at the Standards Committee last week, we set a record for the number of attendees and also the number of papers submitted. In fact, the number of papers submitted last week's committee meeting exceeded the number of papers submitted for all of the standard up to 1998. That's how much the committee has grown. And that's because people are starting to see changes and get very excited about this. So this is the logo of the standard ISO Foundation, which was created because, unlike some other languages, C++ has never had a sugar daddy. C++ has never had a big corporate giant that wanted to spend a lot of money promoting it. It was created by a big giant corporation, AT&T, but AT&T always saw C++ as a language for internal use. and never really spent any money to promote it so that other people would use it. It was entirely promoted by word of mouth. So this foundation was created with the idea of trying to promote C++. One of the things it does is it's created this website called isocpp.org, and you can see all sorts of new stuff. You can see information about the Standards Committee, when Standard Committee meetings are, how you can get involved in the Standards Committee, all those kinds of things. And in fact, there's something on it called the SuperFAC, because this is a merger of the C++ FAC that had come from Usenet and the C++ FAC that Bjarne had personally built on his website, and the two of them were merged together to create the C++ SuperFAC. Another new tool that's come out is a Cross-Platform Ide for C and C++, but I'm not showing you this just because it's a new tool. The reason I'm showing it is because the marketing people that did research before coming up with this product have shared some of their research. So I talked to Anastasia, who published this, who did the research and published it, and said, do you mind if I share this? And the thing she said is, be sure you tell people what our sources were. And what she's saying is, this may be the very best information available on C++ as a language, publicly available. But that doesn't mean it's good. So you have to take all of what I'm about to show you with a grain of salt, because these things are hard to measure. How do we know how many C++ programmers there are? You don't have to have a license, so it's hard to know how many programs there are. But this is what we try to do. The research that they came up with, and this was, remember, this was before, this is probably at this point about 4 or 5 years old, that there were 4.4 million C++ developers in the world, which was a surprise to me because the latest number I'd heard that Bjarne was estimated about 3 million. So this was 50% more than what I had believed was the case. In terms of number of devs, we believe that C++ just barely edges out Python to be probably within the top 4 or 5 languages in use in the world. This has also surprised me a lot because most of the C++ programmers I know live in North America. So what a surprise to find out that there are 50% more in Europe and 50% more also in Asia Pacific. Huge number. Most of this is not Australia. Most of this, of course, is Southeast Asia. And then almost half as many people in Latin America as there are here, or in South America, I should say. What a surprise. There's a huge contingent of C++ programmers in Brazil that we don't really talk with very much. Where C++ is relatively ahead. So one of the things that I work on, C++ Now. C++ Now has a program for accepting applications to become student volunteers. And we will give people financial assistance to attend C++. And the person who runs that program told me that when he sees an impressive resume, well, that could be just an impressive individual, but he's noticing where they consistently get impressive resumes. And they are coming out of Russia, Belarus, Poland, a lot of Eastern Europe, very, very strong in C++. Industry distribution, according to this, it's all about finance. It's possible that the finance really just run a lot of ads. I don't know. But it's not really a lot of surprise. It's where we expect C++ to be used strong. Maybe a few surprises. I was kind of surprised that retail is not huge, but I never really think of C++ as the language of retail. But I've recently met someone who's actually in charge of C++ at Target, the retail store. And they've got a very active operation going on.
Physics isn't in there anywhere.
What's that?
Physics and engineering aren't in there anywhere.
Yeah, and again, it's possible that they're just not they're just not paying for ads and that they didn't show up in the survey. Remember, this data is as good as the sources, and it may not be accurate. All right. One of the things that started again since 2010 is that there's now this audio podcast. How many of you have a commute to work and listen to podcasts on the way to work? I mean, 2 people listen to what? I've been told that the traffic up here is terrible, and that you all have long, hard commutes. Is that not the case?
That's why I work at home.
Oh, you work at home. All right. Well, if you're interested in C++ at all, you really, really want to be listening to the CPP cast, because it's a little hard to listen to CPP cast because they have to read the source to you, and you have to kind of know them. They do interviews, so it's not like you actually have to look at sources. It's a lot of fun, and I really recommend that you take a look. When I put this up, it was episode 145. I think I updated this in June, so that's like almost half a year out of date right there. It's been over 3 years now. There's a new podcast, both a video and audio podcast, and I think you all have our stickers for this. This podcast is Phil Nash, who's a trainer and essentially a developer advocate out of England, and he has a partner, and they do this podcast. They try to do it weekly, but it doesn't really happen weekly very often. But I think it's also a lot of fun. It's not as professionally done as the other podcasts, but it's a lot of fun. And we can get stickers. So there's a number of places where you can find stuff online, a number of communities. There's a lot of Stack Overflow questions related to C++, but Reddit is an incredibly active site. The CPP Reddit, you look at a few of the milestones. It was created just a little bit before 2010, but it didn't really catch on until after 2010 when it hit 10,000 and pretty much adds 10,000 just about every year. And for a while, it was even considered the hot trending topic back in 2018, January 2018. So this is a huge and active site for C++. And I actually kind of flew under my radar until I started working on CPPCon, and we started looking at where our traffic was coming from to visit the website to register for CPPCon, and we saw, wow, we get a lot of stuff from Herb, we get an awful lot of stuff from Reddit. So there's a lot of traffic, a lot of C++ there. Yeah?
Yeah, what happened in January 2018 that it became a trend?
I don't really know. I have no idea what the background is on that. I just know that's if you go on Reddit and look at the history of that, it's possible that it's just a lot of users over a short period of time triggered that it was trending. Either that or it was January, nobody's using Reddit for anything else, so I don't know. There is also cppreference.com. How many of you use that other place where you can see online references? Nobody wants to admit it? Robin's going to admit it? You should know better. This is where we see reference online. Why? Well, one reason is this is a wiki, so it's actually community supported, and it's just amazingly updated. And errors get fixed really fast. I love this. I love this site. Anyway, some other places are the CPP Lang Slack, and in fact, there's an entire channel on CPP Lang Slack that the wiki maintainers of CPP reference are on. But there's a bunch of different channels on Slack. How many of you are on the CPP Lang Slack? How many of you knew about it but just haven't gotten on it yet? How many of you are planning to get on it yet tonight? Okay. No, the people who hang out here include people like Sean Parent and Louis Dion, incredibly bright people in the C++ world actually hang out on Slack, and you can get really high quality answers on a lot of topics. Plus, you can find out if you're going to an event like CPPCon, there's a discussion group about whatever event you have going on. In fact, there's one for local events like this, and you can ask people about how to get people excited about coming in. And there's lots and lots of resources on Slack. You should consider joining that. And there's an auto invite at cpplang.now.sh, because unfortunately Slack is not designed to allow public workspaces. You have to be invited. So if you go to that particular URL, they will generate an invite for you, because Slack doesn't let you do it. Yeah, Rob.
Is that URL something created by Slack?
No, absolutely.
Or someone else created?
Yeah, previous owner created. Yeah, basically you go there and it sends you an invite. It just asks for your email address. You type in your email address and it sends you an invite. So it's not part of Slack, because Slack isn't designed to work this way. Slack is designed to be part of a company, right? And an open community like this is not really what Slack's trying to do, but it's really taken off for us in this community.
Yeah, linear accelerator, Slack. I know that as a linear accelerator lever.
No, SLACK, yeah, Slack.com.
All right.
Go there, get the invite, jump in, pick a bunch of channels, you're gonna have fun. All right, yeah, this is what it looks like. You actually go here, you type in your email, you say, send me my invite, you tell it you're not a robot, send you your invite, and then you can join and go to him. Okay, this is what it looks like. This is CPP Russia. There's just a ton of threads, whatever's interesting to you, all sorts of things. Are you interested in EastConst? If you are, there are wristbands at the back of the room, but just tons and tons of things. Anything you're interested in, there's a group to talk about. This is by no means all of them. This is just the ones that I happen to be a member of. Okay, on the wiki, there's actually a map of where all the user groups are. You can zoom in. If you zoom in, you see the user groups explode out. It just puts them together as they get close. But there's a map of where all the user groups are, and even a calendar of events. This isn't being updated very nicely, but there is a calendar for events. There's a number of different events that have started since 2010. These are new since 2010. Those of you may know Going Native is no longer happening, but CPPCon started 2014, Meeting C++ started 2013, I think, or no, late 2012, and C++ Now also switched from being BoostCon to being C++ Now in 2012, right? And on top of that, we have the Audio Developer Conference, we have C++ Russia. It turns out that the number of conferences is starting to overwhelm me. There's just so many conferences. In fact, there's a list of conferences worldwide, and this is being updated if you go to the C++ file. Okay? So one of our projects in the C++ world is run by our own Robin Kuzman, who is working on captioning videos. We have tons and tons of C++ videos, but they're not captioned or they're auto-captioned, and it turns out auto-capturing of technical lectures is really awful because people don't know what some of our technical terms are, and so it fails. So we need to have these things manually captioned, and then we can work on translations for it, right? So this is a project of Robin's, and I think it's called the Video Access Project, and I put the URL, there's the URL, cppvap.wikidot.com, and you can go there and look at what videos have been captioned and what instructions he has for how you can do capturing. If you're interested in really learning the subject, capturing a video on that subject, captioning a video on that subject is a great way to study it. You're really going to understand it deeply. Okay?
A question.
Yeah.
As I remember, for CPPCon 2017, all the videos have been captioned.
Yes. Yes. I should say that for CPPCon, we've hired a professional company to do captioning for all the videos in 2017.
Is there such plan to do for CPPCon 2018?
Yes. It just takes a while. But yes, it will be done.
Okay.
Alrighty. So I don't know if I was supposed to take an hour and a half, but it looks like I took an hour and a half. Anybody have any questions? Yeah.
You were talking about the interrupts between C++ and server. Would you agree about the compilation system in C++ instead of two-tier compilation system that you see in Java?
You mean having a virtual machine?
Yeah.
Well,
Repeat the question.
what he's saying is, could I comment on contrasting the difference between the compilation system of the model that C++ has, which we compile to native code, as opposed to something like Java, which compiles to a virtual machine. So there's obvious advantages.
And compile to native code.
What's that?
And then compile at runtime to native code.
Yeah. So that the virtual machine has a kind of a just-in-time compiler built into it. Is that what you're saying?
Yeah.
Yeah. I think that there are advantages to an approach where you can say we have this virtual machine, and then you don't have, essentially you can say that everything in Java, there's no such thing as undefined behavior. Everything that happens will have a defined behavior because you're running it against a defined machine. However, I don't think you're going to be able to do that and squeeze out that last little bit of performance. I think you can do pretty well. Java does pretty well. But I don't think you can squeeze out the last bit of performance if you're not compiling down to native code. That's right, because, you're not, as I made the point about the C machine model, which is what C++ uses, right? It's designed around the idea of the way hardware is actually built. And of course, it changes over time, but that's the approach. And it's not written to some idealized machine that's not really the way the world works, but the way we wish to work.
No matter how offensive it gets, you can reach down and that's
Right, that is always the escape hatch in C++. If you really need to do assembly, you can do assembly in C++. Of course, other languages offer that, but we avoid we try to avoid making that necessary. Yeah, any other questions? Maybe one that I can actually answer. Yeah.
Yeah, no, actually, I just wanted to simply back part of your answer regarding virtual machine versus native code. Back in the 90s when Java emerged, and this notion of a virtual machine emerged with Java as well, the justification was that by then developers have to create different ports of the app for different platforms, architectures. And by creating a platform-neutral language based on a Java, on a virtual machine, not a virtual machine, it's like they just care about the language part of that, and then the virtual machine was to traverse the last mile to the target architecture. These days, I can say that I'm seeing like that trend is coming back, perhaps because of something that you mentioned about mobile computing and the need to save battery power, etc. There is a new language that is called Kotlin. It's Google's answer to the case that Oracle made against Google for their use of Java. So Kotlin supposedly can run in the same virtual machine and can even interoperate with Java. But Google is already announcing that they will have a version of Kotlin that will compile straight, to native code.
All right. So if I can summarize, you were talking about that one of the things people were excited about with the virtual machine when Java was introduced is the ability to, you didn't use this phrase, but write once and run everywhere, right? Yeah. The ability to write code that will run on any platform that supports this virtual machine. But you also pointed out that that Java, that Google is now getting behind something that goes kind of back the other way with their new language. Did you call it Gotlin?
It's called Kotlin.
Oh, Golang. Yeah. Okay, I'm sorry. And you said that they are actually they're supporting the virtual machine now, but they've announced that they're planning to compile directly to the native, right? Because that seems, and part of that is to get better performance, battery performance on mobile devices.
Yeah, by the way, they have even announced that Kotlin language is going to be interoperable with C++ in their native version.
Okay, so Golang will be interoperable in C++ in this new world. Okay.
It's called Kotlin. It's K-O-T-L-I-N.
Oh, Kotlin. Okay, yeah. Okay, now I know.
I have an accent. I have to.
No. I'm just slow. What can I say? All right. Any other questions or comments? Well, I've very much appreciated you guys. I thought we had some good discussion, and I hope you enjoy it. Go to the web and download the book. You'll find out that this is only loosely based on the book. There's stuff in the book that's not covered here, and a lot of this stuff is not in the book. And I hope to see you at CPBCon or some other conference. And there's always the possibility I'll be back in the area and talk to you about something else that doesn't necessarily have huge pictures of dragons. All right, thank you.